We've got our robot built up and all the electronics hooked up. Now we got to teach it some dance moves. So if you hooked up your electronics exactly like I did, you'll probably be able to just drop the sample code onto your Arduino and it'll work exactly the same way. Now let's review how the H bridge worked. We've got the A side of the dual H bridge hooked up to the left side motor and the B side hooked up to the right side motor. The IN1 and IN2 pins control the direction of the A H bridge. And IN3 and IN4 control the direction of the B H bridge. So on the A side, to go forward, I need a high on the IN1 pin, which is connected to pin 12 on the Arduino. And I need a low on the IN2 pin, which is connected to pin 13. So to move forward on the left wheel, I simply send a digital write command to pin 12 with a high and pin 13 with a low. Now when I put a high on pin 11, which is connected to the enable A pin, the left motor drives forward. To drive that motor in reverse, I reverse the signal on pins 12 and 13. A low on pin 12 and a high on pin 13. With the B side holding IN3 or pin 8 on the Arduino, high with a low on pin 9 connected to IN4, sets up the B motor to rotate forwards when a high is present on the enable B pin, which is connected to pin 10. An easy way to remember direction was that pin 12 and pin 8 had to be set high for forward on both motors. So once you've set the direction of your motors, pin 11 controls the left motor, pin 10 controls the right motor. So turning either one of them on, either one of them high turns on its corresponding motor full blast. As an option, instead of digital write on pin 10 or 11 to spin the motor full blast, you can use the analog write command on those pins to send a pulse width modulated signal instead, thus controlling the motor speed. What we'll do first is try and drive a straight line, and we'll use PWM to control the speed, keep it slow and moving in a small space. This will also magnify a problem that I want to point out. I got to try and keep all the action right in this small area on this tabletop to keep it within the camera's view, but you can run yours on the floor or a big tabletop, whatever. The first sketch you can download from the download section is called Calibration Straight Line. You can just copy and paste it into a new sketch if you'd like. All this does is it sets up the control pins as outputs, and then it drives both motors in a forward direction at approximately half speed with about a 50% duty cycle on the PWM. It then stops the motors, waits a second, and then drives the motors backwards. Now, because both motors are being commanded with the exact same commands and duty cycle, theoretically, it should drive a straight line. So let's flash our Arduino with this sketch and see what happens. Now, to flash it, watch what happens when I plug in the USB cable. It's running a previous sketch I had in it for testing, so it starts to turn the motors even though I have the battery power off. So right now the power from the computer is powering the Arduino, which is backfeeding power to our H-bridge and to our motors. Now the Arduino simply can't handle that kind of current draw, so it's very important that you power up the H-bridge with the batteries. Either hit the ON/OFF switch to the ON position, or pop your batteries in if you don't have the switch, then you can either just hold your robot while you program it, or, you know, prop it up on a box or a block of wood so the wheels are off the ground. So go ahead, flash your sketch to the Arduino, then unplug the USB and turn off the power. Now, this sketch is a simple test for two things. To see if you've got any wiring problems, either a motor wired backwards or a wire disconnected, whatever. The second thing, well, let me run mine so you'll see for yourself. When I turn it on and it is commanded to go forward in a straight line, well, that's not very straight. Man, reverse isn't much better. Seriously, what on earth is going on here? Well, all of this manufacturing of all these parts, the wheels, the motors, the gears in the gear drives, they're all imperfect. No two motors, no two wheels are alike. And so in any case, one motor just turns far more freely than the other. In fact, the left motor on mine is so stiff, it has a habit of actually stalling when the PWM gets any lower than about 150. It is more than likely that you'll have one motor that turns faster than the other. Now, it might be as bad as mine, it might not. So I can play with the numbers and basically calibrate the sketch to compensate. I just take a guess. In my case, it's obviously the left motor that's giving me issues. So I'm going to crank up the PWM until, in the words of Thanos, it's perfectly balanced, as all things should be. Now, I experimented around a lot before filming this, and so I was able to figure out a fudge factor here. Although through experimentation, I found that if the right motor was at 125 and the left motor was at 165, it was pretty much balanced. Now, understand it will never be perfect. This table surface is actually very slippery. When operating my robot at full power, I can literally see the right wheel spinning out while the left wheel holds its traction. So that can veer the robot one way or the other. This dolly wheel on the back can be stiff on its spinning. So it can be stuck, skewing the robot one way or the other. Or even when the robot is just switching from a forward direction to a backward direction, this dolly wheel has to spin around. While it's turning, it's changing the direction of the robot. So it'll never be perfect, and for what we want to do, that's perfectly acceptable. If you were attempting complex obstacle navigation, you can now see why you would want those encoder wheels on your drive shafts, as it will tell you how far each wheel has turned. But even that lies, because one wheel might have, you know, more air in it than the other, and thus be a larger diameter. It might only be a millimeter difference, but a millimeter difference is 3.5 millimeters in the distance traveled per rotation. So even if your encoder says the wheels have both traveled exactly 1 meter, one wheel has actually traveled 1.5 centimeters farther. And so it accumulates over time. The farther you travel, the more the error. So as you can see, it's always an imperfect system. Now, we'll get into all of this in detail in the 5th course on autonomous robots, where we experiment around with self-navigated robots and cars using artificial intelligence and various navigation techniques with or without the aid of GPS. But I digress. So I have a number I'm going to use in my next sketch, where we attempt to drive the robot in a figure 8. We'll start here on the figure 8, first traveling a short, straight line. And to turn, we'll simply vary the speed of the motors using PWM. we make a forward moving right hand turn by either speeding up the left motor or slowing down the right motor. So to make a forward moving left hand turn, we either speed up the right motor or slow down the left motor. So in my case and in my sample sketch, Robot Figure 8, which you can download from the downloads section, I slowed down one of the motors to make a turn. And this is just to keep it all under control and moving at a nice slow speed. So when you look at my sketch, I start off on the straight line stretch in the middle of the figure 8, and the downloadable sketch has the stock PWM values of 125. Your robot may actually run a very straight line, and so you don't need to change these numbers. Mine doesn't, so I actually alter these numbers so that on the straight legs of the figure 8, it matches what I discovered when I ran the calibration sketch. Now also, I'm glad that my robot is such an extreme case because it gives me the opportunity to show you how I compensate in the program. I'm simply timing all movements to approximate the figure 8. The right drive motor of mine is so much stronger than the left that I actually altered these delay times in the turns because it would complete its right-hand turn far faster than the left-hand turn. So you'll simply have to experiment and play around to see how your robot performs. There will always be variation. Motor conditions, tire wear. The biggest factor will be the battery conditions. If your robot has two motors that are really fast, you may need to turn down the delay on the figure 8 straight legs because it's traveling too far on the straight legs. I don't know. You'll simply have to play with it to find out. So I'll modify my numbers in my sketch and simply experiment with the delay times. After a lot of experimenting, I got mine going in a fairly decent figure 8. Now it wanders to be sure, and I could experiment more to get it more precise, but I'm simply changing the times for how long I drive in a straight line and how long I turn. This is all we're going to do when we use our infrared sensor as a proximity detector. And in fact, this is pretty much all that the robotic vacuum cleaner, the Roomba, does. It has a sensor on its front. It drives around the room at random, vacuuming as it goes. When it bumps into its proximity sensor, it backs up and turns for a set time, and then goes forward again until it reaches another obstacle. So any navigation we perform will be very simple like this. And we simply time the movements approximately. Okay, we got a dance party for that our robot's going to, so we need to teach it some dance moves. You can download the sample sketch from the downloads if you want, or you can just make your own sketch. It's quite simple, really. In my Dance Party 1 sketch, I just went straight up full power. Either the motors were on or off. Because I was making fast, short movements, the robot didn't really go very far, so I didn't need to slow the motors down to use using PWM. So I first set all the control pins as outputs like before, and now I need to decide what movements I'm going to do and at what speed. Now, an interesting thing you can try here, you can just make random moves in 4-beat sequences. And it'll surprise you how your robot's movements will line up with just about any music you play. However, with a bit of effort, you can also put together a pretty complex dance routine in predetermined time with some music. So I picked a nice funky 70s tune, and it had about 110 beats per minute. Well, 60 seconds divided by 110 is 0.55 seconds. We're using the delay command. in the sketch to time our moves. So I just tried to time everything in multiples of delay 550. Now it's approximate. Some of my times were, a little different to compensate for start and stop times of the motors or wheel slip for fast movements, etc. But it was amazing how much of the movements lined up with the beats in the music by simply timing all movements into multiples of approximately 550 milliseconds. So I upload my Dance Dance Party sketch to the Arduino. Let's clear the dance floor and cue the music. Okay, that's enough of that. You get the point. Just take a look at my code and you'll see it's very simple. In fact, you can cut and paste any of these sequences to build one long sequence like I did. I did a series of forward, backward, straight movements, a do-si-do spin around, some right, left spins, and backward movements, all based on timing. So if you just take this sketch and flash it onto your Arduino, play any music that is approximately 110 beats per minute or a multiple thereof, and you'll be surprised at how well its dance lines up with the music. If you have different music, just figure out how many beats per minute it is, like I did, and just count your millisecond intervals you need to line up with the beats in the music. Change all of your delay times and just play with it, building up a dance sequence. Ask yourself, okay, what moves do I want to make? And then program that sequence by simply setting the control pins for forward or backward movement on your two motors, then timing, how long you want to make that movement. Simple, huh?